Good to bad. When industrial protocol translation goes wrong, this was a project done by myself, Marco, Luca, Ryan, Philip, and Reiner, all at Trend Micro. So we are talking primarily about protocol gateways, and the two different types of protocol gateways that we looked at are real-time gateways and data stations. And so the real-time gateways typically do a packet in, translate, packet out. The data stations do essentially kind of a continuous monitoring or continuous read of the PLC, and then store that information into the data station's memory. The operator would then, or the HMI would then query the data station, and then the data station responds to that query from its own internal memory. If the operator wants to change a value, the value is set within the data station's memory, and then the data station will generate a query to the PLC a couple seconds later. And for these, the actual translation, they can be from Modbus to Ethernet IP to BACnet. There's multiple protocol translators out there, or protocol gateways out there that do translations between various types of protocols. You can also do it between Ethernet and serial, Ethernet to Ethernet, or serial to serial. Just depends on what you're trying to translate. So the approach that we had to our research, we got about 5 of these different protocol gateways, and we set up a simulator on one side, we had the researcher on the other, and we added a fuzzer, and I'll talk a bit about the fuzzer in a little bit. And the fuzzer is able to, generates the test cases. It's also able to do monitoring for crashes. We would then, we had a sniffer set up. The sniffer and the fuzzer would feed data to an analyzer, and the analyzer would then give a report back to myself and my colleagues. So for fuzzing, there's 2 general types of fuzzing. There's the mutation-based fuzzing, which you take a file or a packet that you captured, and then you alter that packet or that file while opening the application or while sending it to the service, and you see if you can get any crashes based on that or anomalous activity. There's also generation-based fuzzing, which is what we used, and that is to you look at the specification and then you generate test cases based off of that specification. We used BooFuzz, which is a fork of Sully, which has been around for a number of years. And we specifically based our initial testing off of Mr. Youngcraft's BooFuzz Modbus that he had on GitHub. So taking a quick look at what the fuzzer looks like, you essentially initialize whatever you want to call this particular fuzzer. Then you would go through, you generate, so for this we were doing Modbus primarily. So you have a transaction ID, the protocol ID, the size of the payload, and the slave ID, and you can configure what of those you want to actually fuzz. And then within the payload, we have the function code, the address of, in this case, it's a write single coil. So the address of the coil, and then the value that we're sending the coil. So it would be a 1 or a 0. And then we go through and send the packet. On the instrumentation side of the fuzzer, we have, you can monitor to see if the device is alive or if it's crashed. So we would essentially connect to the target, see if it's up and running. We would send our test case, connect back, and then if the device is still up and running, we'd go on to the next test case. If the device has crashed, we would then force a reboot, wait, and then continue on testing the next test case. And you would also get a log to see that something crashed. So for our sniffers, we used Wireshark, and we used a tool called IO Ninja, and we used IO Ninja for the serial interface side. It worked out really well. So we would take those two packet captures and throw them into our analyzer and do a little bit of data normalization on them so that we could actually do some analysis. And our analyzer was pretty much just some Python scripts that we threw together, but it would do analysis for mismatched or dropped packets, and it would do correlation based on the timestamps for the real-time gateways, because again, it was packet in, translate, packet out, so it was really easy to correlate based on time. For the data stations, we had to throw in some kind of nonces, some certain values that we could detect when it would actually send the packet to the PLC or to our simulator. So if you look here on the right-hand side, you can see, you can compare kind of the key data, the actual payload that was being sent, as well as you can see all the junk on the prepended to the Modbus. So it has the transaction ID, the protocol ID, and the size for the Modbus TCP side. And then you can see all of the, or you can see the RTU CRC junk at the end on the Modbus RTU side. So moving on to what we actually found. Within the real-time gateways, we had about 5,000 invalid packets that we sent, and about from the TCP to RTU side. So that's translating from Modbus TCP and going to Modbus RTU. And then we had about 2,000 RTU to TCP side or packets. So within the Modbus TCP, on the next COM, it basically didn't do any filtering of packets of invalid or malformed packets. It would essentially just forward on those packets. The Schneider and the Digi one both cut out about 55 to 60% of the traffic that was invalid. On the RTU side, the Nextcom did quite a bit better. It filtered out almost 20%, as well as the Schneider, and then the Digi only filtered out about 9%. So one of the interesting aspects is that is this packet down below, and I'm going to go into a bit more detail. So it has an incorrect message length, and that allows the so it would send that packet as is to the PLC. Now, if the PLC doesn't recognize the packet, it would probably just drop it or ignore it. But if you do something kind of interesting and you craft special packets, you can actually cause the PLC to respond correctly. So in this instance, in the green, you can see that we have what would look like a read input register packet, but it just has the incorrect message length. When it goes through the protocol gateway, it comes out looking exactly the same, but in Modbus RTU, that actually looks like a write multiple coil packet with the correct length, with all of the valid data in there. So if you had a firewall on there that isn't protocol aware, that doesn't do really good handling of, or checks for validity of Modbus packets, the packet would actually get through the firewall, and would then, you could then do a write multiple coil to the PLC. Because a lot of the IDSs and some firewalls will just do kind of a basic inspection to see if it's a function code 5, function code 6, 15, or 16 in order to see whether or not you're allowed to do a write, or it might create an alert, or it might try to stop it depending on what the firewall or IDS is configured to do. So moving on to data stations. Data stations are kind of interesting because they have this IO mapping table. So you set up a kind of the input and the output, and it does everything within the memory. So what we found is that in the Moxa, there's an arbitrary read-write vulnerability within this IO mapping table. And what happens is that a message coming in has an index, it's an inbound message used as an index in the mapping table. And I'm going to show you what that looks like in just a minute here. But what that allows you to do is an out-of-bound write, and it doesn't do a check on the function codes. So what happens is, if you see down in this right-hand corner, up top, we have these Modbus commands. We have one called set SW1, another called set crit temp. If you look in the lower right-hand corner, you'll see we have the actual internal addresses for these for this function. We have an internal address of 00 and 2 to 3. So set S1 or SW1 is a 1-byte address, and the set crit temp is a 2-byte address. And what happens is, when you send a Modbus packet of function code 5 to write a single coil, and you give it an address value outside of the range for that internal address 0, which is what we had set for that set SW1, it will actually overwrite into the internal address 2. So this one is writing an output address of 16. Or hex 16, which is actually 22. There's an offset of 1, which gives you 23 as the internal address. So it then changes the internal address of the address number 2, the value of address number 2, and you get a register setting or a register value that has been changed when you just did a write coil. So there's no protection of the memory. So what the actual impact of that is that you can arbitrarily read and write in the memory, and a write coil can go to an address outside of its boundary. It allows you for a write coil to send a write register command effectively, or a write register command to send a write coil command. And then you can do like a write multiple coil, which allows you to send overwrite coils as well as overwrite memory. And then, so that's it as far as the actual major translation vulnerabilities that we had. There were other issues that we found as we were going through this this process, and so we had some. You can extract the IO table from the data stations, denial of services, a root shell that with some authentication, and credential reuse, memory leakage. There's kind of all different types of vulnerabilities that we found with these devices, but our main focus was on that, the translation vulnerabilities. So if you want to take a look, we have a very detailed paper on on our site. There's the white paper has a bit of details. This goes into, I think it's like a 60-something page, goes into all of the details of what we found within the protocol gateway vulnerabilities. So that's it for me. If you have any questions, please feel free.